Welcome to the world of acids and bases. I feel like it's a disservice if you graduate from a high school chemistry class and you don't know what an acid or a base is. So here it is. All your hopes and dreams are about to come true, right? Acids and bases are all kind of a battle of hydrogen ions versus hydroxide ions. Who wins the battle will determine whether the final solution is an acid or a base. In general, some properties of acids may include a sour taste. Not that I would use that as a laboratory test to see if something is an acid or a base. I'd maybe use like pH or something like that. But I mean, when we think about acids, it's usually things that are kind of sour, like citric acid and in citrus fruits, or acid in some drinks. Acids tend to react with metals and produce hydrogen gas. H2, diatomic hydrogen gas. For example, the reaction that we've done a few times throughout the year is that zinc in hydrochloric acid. Well, remember, like the zinc kind of replaces the hydrogen. The hydrogen gets the boot, becomes the single element diatomic, and then zinc comes in to bond with the chlorine. And technically, so that we can sleep well tonight, the zinc is +2 and the chlorine's -1. And so I need 2 chlorine, which then means I need a 2 by the HCl. Not that it really matters, but yeah, and this could happen with all kinds of different metals. As long as it's a metal that's more reactive than hydrogen, right? Then we should get this typical reaction where hydrogen gas would be formed. Now, on a particle level, acids are solutions that contain hydrogen ions. They're going to look like little H+1 ions. So the acid is the hydrogen donor. We're concerned with solutions that have hydrogen ions. Now, sometimes the hydrogen will just be like a free-floating H+1 ion, but sometimes that hydrogen ion is attracted to a water molecule. And when that hydrogen ion kind of attaches to the water molecule, we see it looks like this, H3O +1, and we call it hydronium. Hydronium. And so you might see a question referring to like how much hydrogen is in a solution, how much hydronium is in a solution. It's really kind of the same thing, because this hydronium is just a hydrogen ion that has attached itself to a water molecule. Now, here's the why behind that. So we know that water molecules are like these little Mickey Mouse heads, and this is maybe like the oxygen and the 2 hydrogens. And we know that water molecules are very polar, that the bond between hydrogen and oxygen is polar. Oxygen, having that high electronegativity, seems to draw electrons toward himself, so that the oxygen end of a water molecule is partially negative, and the little baby hydrogen ends are partially positive. Well, now enter in this hydrogen ion. So I've got these hydrogen ions that are in solution, which means that they're in with water. And so here's this little adorable hydrogen +1 ion, and it finds itself attracted to the water molecule. So whenever this hydrogen +1 ion is kind of near a water molecule, there's attraction between the partial negative end of the water molecule, and then this ion is positive. And sometimes that attraction becomes so strong that this little individual hydrogen ion will just attach itself to the oxygen end of the water molecule. We call that then hydronium, H3O, which it is +1 now. There is a charge. Water was neutral initially, but with an extra +1 hydrogen. The water is now a H3O plus 1 ion. Cool. Now we are going to use some similar terminology that we used back in the solution unit, because really acids and bases are just special solutions. An acid is a solution that contains hydrogen ions. A strong acid is just an acid that completely dissociates to form those hydrogen ions. So in the last unit, we mentioned the term strong electrolyte as just anything that completely dissociates in solution. Well, now it's saying strong acid. The strong part means it totally dissociates. Acid means one of the ions is hydrogen. So one of the best examples of a strong acid that we'll use is that HCl hydrochloric acid. If I were to write this as like a little equation, it would dissociate to form hydrogen plus 1 and chlorine minus 1. And that happens 100%. So the strong part refers to the tendency of dissociation. Strong means 100%. Everybody splits. There will be no neutral HCl molecules. It's all hydrogen and chlorine ions. So the strong means 100% dissociation. Strong acid means that one of the ions produced is hydrogen. So like in the last unit, we would have said something like sodium chloride is a strong electrolyte. Sodium chloride dissociates 100% to form sodium and chlorine ions. Well, now we could say that this is a strong electrolyte because it dissociates completely, but we could just be a little bit more specific by saying strong acid. One of the ions is hydrogen. Cool. Now, similar, we can say that a weak solution or a weak electrolyte means that there is not a full dissociation. Same thing if I talk about a weak acid. So a weak acid is a particle that's going to produce hydrogen. I mean, acid means hydrogen is in the solution, but weak means that it only partially dissociates. There's not a full dissociation of the acid. Some particles will stay neutral. And maybe one of the best examples that we'll use in the lab is acetic acid. Its formula is CH3COOH. Acetic acid. It sure doesn't look like an acid. I mean, you think acids have all this hydrogen, and there is hydrogen. But you put this thing in water, and here's what happens. Now, I'm going to put water in the equation, just like what we did for weak electrolytes, where weak electrolytes are particles that don't normally just dissociate and form all these ions, that they tend to have to react with the water in order to get any kind of a charged particle produced. Same thing here. And in fact, this example was given to us back in the solution unit. We just didn't call it an acid. We called it a weak electrolyte. We totally use this in the lab. When that acetic acid is in water, the negative end of the water molecule, so we know that the oxygen end is the negative end, it's attracted to things that are positive. Well, this little hydrogen that's dangling off the end of the acid is positive. So there's attraction. Here's that partially positive hydrogen, and there's the partially negative oxygen. If these particles are in the right place at the right time, in the right orientation, and the attraction becomes strong enough, this hydrogen can get totally ripped off, and it becomes part of the water molecule. When that happens, then, you're left with something that looks like CH3COO, the hydrogen is gone. That thing used to be neutral, but now if it's missing its hydrogen, it becomes negatively charged. We could say negative or -1. The other particle, well, now it's a water molecule with a hydrogen. It's that H3O plus 1. It's that funky hydronium ion. Oh. Well, in the end, whether the hydrogen is free floating all by itself, or if the hydrogen is attached to a water molecule, as in the hydronium ion, both are the sign of an acid. It's just that now in this second reaction, this doesn't happen very often. This might only happen maybe like 1% of the time, where most of the particles would be neutral acetic acid molecules. And only if that acid molecule just butts up right next to a water molecule in the right orientation and the attraction is strong enough, only then will that last hydrogen be removed. It just doesn't happen every time. Maybe only 1 out of 100. That's the weak part. Weak refers to the reactant side. Weak refers to the tendency to dissociate. The acid part comes from the product side. That if hydrogen or hydronium is produced, it's an acid. Cool. In the lab, then, we'll be able to kind of look at how that changes the properties of the acid. Depending on how much hydrogen is in the solution, how might hydrochloric acid react differently than acetic acid? Now, bases, again, not that I would taste them, but maybe, I don't know, maybe we'd say bitter. They do tend to feel slippery. But again, like a laboratory test would not involve me dunking my hand in a solution to be like, oh yeah, it's a little bit greasy, it's a little oily, it's a little slippery, it must be a base. Probably not the best choice. Bases are our hydroxide producers, OH -1. We tend to produce hydroxide, a polyatomic ion. Cool. And now the whole strong, weak stuff is really similar. Strong bases will completely dissociate to form hydroxide ions. One of the best examples that we'll use in the lab is sodium hydroxide. It dissociates completely to produce sodium ions +1 and hydroxide -1. And that happens 100%. In a beaker of sodium hydroxide, there will be no neutral combined sodium hydroxide molecules. Everybody splits. Everybody splits to form sodium ions and hydroxide ions. So again, the strong part refers to the reactant side. How completely is this particle breaking apart and dissociating? The base part comes from the product side. If we see hydroxide as one of our ions, we say strong base. Weak bases then will produce hydroxide, but just not completely. Weak. They'll partially dissociate in water. They tend to have to react with water in order to form these hydroxide ions, and it just doesn't happen all that often. The one that we'll use most often, this one's kind of funky. It's Nh3 Ammonia. Probably the most common example of a weak base that we'll use in the lab. Here's what it does. So you put ammonia in water. And the Nh3 molecule on its own really does not have a tendency to dissociate. It kind of tends to stay neutral. But you put that bad boy in water, and you get kind of a strange reaction. So again, we know that hydrogen tends to be kind of a partially positive charge, and oxygen ends up being partially negative. That in there, partial positive, partial negative. Well, in the ammonia molecule, the negative charge ends up falling on the nitrogen. The nitrogen also carries a pretty high electronegativity, and the hydrogen is partially positive. I mean, nitrogen also tends to have like, a lone pair on the top, and then we have these little 3 single electrons where we put the little hydrogens. 1, 2. Oh, can I squeeze one in? Sure. 3. I mean, there's what it looks like. And so you've got nitrogen with a pretty high electronegativity, and there's a lone pair up on top. So the nitrogen region becomes pretty negative. Well, this time, it's the nitrogen that tends to remove a hydrogen from water. What? This is crazy. Now, you will never have to write this equation yourself. It'll be given to you. We just have to understand what's going on. And so when this happens, where the negative nitrogen becomes so attracted to a water molecule that at times the hydrogen is just ripped off, you end up with something that looks like NH4, which now with an extra hydrogen is charged +1. It's that ammonium ion. And then from water, all we have left is 1 hydrogen and 1 oxygen. And we typically write that as OH. And since it's missing a positive hydrogen, the remaining charge is -1. Whoa. This is weird. And again, you never have to write this equation. But if you saw this equation and they say, hey, is this acid, base, or neutral, or something wacky, you'd be able to look at that product side and be like, well, what do you know? It's a base. One of the ions produced is hydroxide. That thing's a base. And it's kind of tricky because NH3 doesn't scream base. Like, I mean, if I'm looking for OH hydroxide to be the sign of a base, I can look at sodium hydroxide and I can get that right away. Yeah, there's hydroxide. It's a base. But when I look at NH3, I don't see OH. And so I don't usually think, oh, for sure, that's a base. A base just means that hydroxide is produced in the solution. It's got to be on the product side. Well, it's actually coming from the water. Wacky. The hydroxide is what's left over from the water once we remove a hydrogen. And so as long as there's hydroxide present, it doesn't matter if it comes from the original particle or if it comes from water. If there's OH on the product side, it's a base. Now, it's a weak base only because this just doesn't happen every time. This might be a 1% chance that most of the NH3 molecules and water molecules will remain neutral and they just kind of coexist. But if they're in the right orientation and that nitrogen is really close to the hydrogen end of the water molecule and that attraction becomes strong enough, it's possible to remove the hydrogen from water. Then we're left with the hydroxide, indicating that the remaining solution would be a base, a weak base. It just doesn't happen very often.